All right, welcome everyone, and a special shout out to Mr. Wilf's discrete math class. Today, we are jumping headfirst into a really core concept, vertex edge graphs. And trust me, once you see it, you're going to start seeing it everywhere. It's this amazing way to model relationships, and it all kicked off with a surprisingly tricky puzzle from a long, long time ago. So let's wind the clock back to the 1700s, to a town in Prussia called Königsberg. It was a pretty unique place, built around a river with two big islands right in the middle. And to get around, the town had 7 bridges connecting everything up.
Well, the people there came up with a little brain teaser. They started wondering, is it even possible to take a walk through town that crosses every single one of those 7 bridges? But, and here's the catch, you can only cross each bridge one time. What do you think? Could you figure out a path?
Okay, so here's the map. You've got the north and south banks of the river, and then the 2 islands, 4 separate pieces of land in total. And you can see all 7 bridges connecting them in different ways. The rules are simple, right? Start anywhere you want. Your goal is to cross all 7 bridges, but you can't recross any of them.
Now, this puzzle actually stumped people for a long time, until it got to a genius mathematician named Leonhard Euler. And his big breakthrough was realizing that looking at the map, the rivers, the streets, it was all just noise. The real answer was hidden in the connections themselves. So here's what he did. First, he just simplified everything. He said, look, each piece of land, the 2 banks and the 2 islands, let's just think of them as a single point, a dot. It doesn't matter how big they are or what's on them, they're just locations.
And then, and this is the aha moment, he got rid of the map entirely. And what are you left with? Just this, 4 dots and 7 lines. The dots are the land, and the lines are the bridges. This simple little drawing has all the information you actually need to solve the whole thing.
This was it. This was Euler's big idea. He boiled the entire messy, real-world problem down to its absolute essence. What are the things, and how are they connected? And by doing this, he basically invented an entire new branch of mathematics that we now call graph theory.
So this dot and line thing that Euler came up with, it has a proper name. It's called a graph. Let's break down exactly what that means, especially for what you'll be doing in discrete math.
In math, a graph is just a way to model relationships, and you only need 2 ingredients to make one. That's it. Just 2 things, vertices and edges. First, you've got your vertices. You might also hear them called nodes. These are just the objects, the things in your problem. For the Königsberg puzzle, our 4 vertices were the 4 landmasses. Simple as that.
And second, you have your edges. These are the lines that show the connection or the relationship between 2 vertices. In our puzzle, the 7 bridges were the 7 edges connecting the dots.
Okay, I have to stop here for a super important point. When Mr. Wilf says graph in this class, he means this, dots and lines, vertices, and edges. He is not talking about the kind of graph you learned about in algebra, plotting y equals x squared on an xy axis. Same word, totally different idea, don't get them mixed up. So who cares about an old puzzle from the 1700s? Well, it turns out that this simple idea of dots and lines is one of the most powerful tools we have for understanding our modern world. It's literally everywhere. And we can make our models even smarter. See, an edge can just be a connection, or it can have a direction. We call that a directed graph. Think of it like this. A handshake is undirected. It goes both ways. But owing someone money, that's directed. It's a one-way street from you to them. And this is what's so cool about it. This one single idea can be used to map out social networks, plan flight routes, understand chemical bonds in a molecule. You can even use it to map out the entire internet with websites as vertices and links as edges. Let's make it super simple. Think about a social network, right? Every person with a profile is a vertex. And if you're friends with someone, boom, you draw an edge between your 2 vertices. It's a perfect picture of the entire friend network. Or what about planning a big project? This is something you'll definitely see more of. Every single task you need to do is a vertex. And if you have to finish task A before you can even start task B, you draw a directed edge, an arrow, from A to B. This gives you a clear map of what has to happen and when. But the best part about all this is that you can do it too. Now that you know the basic ingredients, vertices and edges, you can start looking at problems in a whole new way.
you can start seeing the hidden connections in everything. And here's a really simple way to start. When you're faced with a problem, just ask yourself 3 questions. 1, what are the main things or objects here? Those are your vertices. 2, how are they connected or related? Those are your edges. And 3, let's draw it. Just seeing the picture can often show you the answer right away.
You could use this like today. Think about all the errands you have to run after school. The library, the grocery store, your friend's house. Each one is a vertex. The streets connecting them are the edges. And you can even add more data, like the time it takes to drive each street. That becomes the weight of the edge. And suddenly the question is, what's the fastest path to hit all my spots? Because that's really the big idea here. Our world, from our friendships to the entire global economy, is just a giant series of networks. And vertex edge graphs, well, they give you the map to understand it all. Oh, and the Königsberg Bridge problem? Euler proved it's impossible. See, he figured out that to make a walk like that, you can have at most 2 land masses, 2 vertices, with an odd number of bridges connected to them. Königsberg's graph, all 4 vertices had an odd number of edges, so it was unwalkable from the very start. And discovering that simple rule, well, that's the power you get when you start thinking in graphs.